Okay, hi everyone. So what we're going to be doing here is looking at some of the tutorial exercises from the chapter on stability. So in the webinars and the seminars today, we've looked at the stability function of implicit and explicit methods. So I'm going to be showing you how we can use MATLAB to help us with that. Okay, right. So I've started recording. Hopefully that's started. I've also had a couple of bits of feedback regarding the use of that document camera in the last webinar. I understand it is problematic and it's not an ideal solution. So we'll see if I can source a stylus so I can so it can be much clearer. So I'm looking into that. Okay. You guys all there? Or am I talking to? Okay, I'm assuming you're there. Right. Sorry about that. It's yeah. Okay. Right. What I'm going to do is I'm going to share my screen, and I'm going to share. Oh, crikey! I've got loads of things open here. Find out what I need to share. Okay. Right. Can you all see essentially what is a MATLAB live script? So this is the live script. It's called the I labeled it D_stability. Okay, so you might be wondering why I don't label them 1, 2, 3, etc. MATLAB doesn't like you to start a file name with a number, so hence why it's A, B, C, D. So this live script is it's available. I mean, you can download it from the Moodle area. Okay, and right at the bottom, you've got some exercises. So I'm just going to show you how we can use MATLAB to help us determine stability functions and stability analysis for Runge-Kutta methods. So this is the first question. Okay, so we have an explicit method. We know it's explicit because our A matrix is lower triangular. Okay, remember what I said about this would normally have a partition. So between the first and second column and between the last row and the rest, there would normally be a partition here, but MATLAB doesn't like that for some reason. Okay, so what I'm going to do is just show you how we can use MATLAB to determine that stability function. And so first thing I'm going to do is define the ERK method. And essentially what this means is just entering what our A matrix is. So here we have a 5-stage method. So I'm going to enter in the A. This is this matrix here. Okay, just enter it in. Try and do that as quick as I can. 1/4, and I've got 2 noughts, and we've got 0, 1/6, minus 1/3, 1/6, and 0. Okay, so that's my A matrix. Just going to press F5 just to check that that's working. It's taking a while. Okay, so there we go. So you can see that I've got a lower triangular matrix A. Then I'm going to enter in the B matrix. Yeah, B matrix. So remember, we assumed that the B array or the B vector is a column vector. So I'm going to put semicolons between each element of the B vector. Okay, and I'm also going to define my vector of e's, vector of ones, which is ones, and I've got 5 stages, and I want 1 column. So if I just run that to show you what that output gives us, you can see that just gives us a column of ones. Okay, so I've defined the method. So explicit Runge-Kutta method. Okay, so this is our stability function. So this is equation 4.5, and essentially the as I mentioned before, the coefficients of z or z squared, z to the power 3, it's B transpose times A to the power k minus 1 times E. So we're just going to use MATLAB to do all the heavy lifting for us. Let's go right down to the bottom again. Okay. So So if I look at the coefficient of Z, so that was just B transpose times E, which is essentially summing all the values of B transpose. So we've got the coefficient. I'll put list them. So coefficient of Z power K. So that's coefficient of Z. Coefficient of Z squared is B times A times E. And if I run that, it could give me as 0.5, but I'm going to convert that to a fraction by using the rats command. There you go, it's a half. Coefficient of Z cubed. So this is A squared times E. Okay, so all I'm going to do now is just I'm just going to increment the power of A and rats beats times A power 3 times E, and then do a couple more. Okay, so you can see these are my coefficients of the various values of Z. So what I'm going to do, I'm going to put them together. So I'm just going to write them in an equation. So we've got 1 plus Z plus half Z squared plus a 6 Z cubed plus 1 over 24 Z power 4 plus 0 Z power 5. Okay, so that was the that's the stability function for this Runge-Kutta method. Okay, so that's the stability function. You can see that this agrees to the series expansion of e to the z up to the 4th order term. Okay, so you can see that it doesn't agree to the 5th order term because this will be 1 over 120. That'll be 5 factorial. So this is a 4th order method. So this is a 4th order method. So even though it's got 5 stages, even though this method had 5 stages, it's actually only 4th order accurate. Okay, so that's how you can use MATLAB to do all the matrix multiplication. So, for example, a 4th power of a 5 by 5 matrix is no fun to do by hand. Okay, has anybody got any questions about what I've just shown you about the stability function for an ERK method? Okay, I'll move on then. Okay, so here we've got another question. Determine the stability function for a Runge-Kutta method. Now, as I mentioned in the earlier webinar, in the assessment, I want you to do that by hand. Okay, so I'm going to do this using MATLAB. Now, you're welcome to use MATLAB to check that your hand calculations are correct. Okay, but when you submit your assignment, I want to see the actual individual working out. So, and we want that typed up as well. We want to see it professionally presented. Okay, so first thing we do again is for this question is define our IRK method. So here we've got a 2-stage method. So I'm going to define my A matrix. Okay. And I'm going to define actually I'm going to call it EBT. Okay, so I'm just going to pause there for a sec and then go back to equation 4.7. Okay, so this is the stability function as we used that in the last webinar. Okay, so remember that EBT is a diagonal matrix with elements of B on the main diagonal. Okay, so that's what we've got to define. So I'm going to call it EBT. Sometimes people call it just B, but it can be quite misleading. So B1 and B2 are both a half. Okay, so that's our IRK method. Okay, so now what I'm going to do is I'm going to determine PZ and QZ. Now, I'm going to use functions for these. Okay, so it's a little trick you can do here. So the first function is p. Now this was the numerator, and if I go p equals at, oh, can't get the at symbol, at z. Okay, so this means I'm defining a function, and what I have forgotten to do is actually say that z is a symbolic variable. And my function is going to be the determinant of the identity matrix. So here we've got 2 by 2 matrices, so we need a 2 by 2 identity, minus z, and that's multiplied by a minus EBT. Okay, so that's defined the function, and I'm also going to do the same for q. So q is at z, so I've got the determinant of the identity minus z times a. Now that was just equation 4.7 for these. So p was the numerator and q was the denominator. Okay, so if you want to see what these are, if I just, oops, can't type today. Okay, so if I just return pz, you can see we have one, well, z squared over 12 plus z over 2 plus 1. Okay, so that's done all that sort of work for us. And if I do the same for qz, see what that is. Okay, quite similar actually. So you can see it's actually the same apart from that sign there. Okay, so this is just, I mean, you could do that by hand. They're only 2 by 2 matrices, so they're not too tricky. So excuse me, what I'm going to call it, too many R's. Okay, our RZ function is PZ divided by QZ. Okay, now what MATLAB will do here, it will try and, oh, I was saying it was going to try and simplify it. No, okay, it's given us in this form. Sometimes it does try and simplify it, sometimes it gives it to you in a much too complicated way and you then have to manually simplify it yourself. But in this case, we're lucky, it's given it to us in a nice manner. So that's our stability function for this run cutter method. Is this a stable method or not? So first thing we've got to do is calculate the roots of QZ. And this is dead easy with MATLAB. So we simply do solve QZ equals 0. Okay, and that will give us the roots of QZ. There we go. So we got roots of 3 plus or minus root 3 times I. So remember, we're only interested in the real part of the roots. So you can see both real parts are 3. That's positive. That's greater than 0. So that first criteria I mentioned earlier is passed. In other words, the roots of QZ have to exist in the right-hand side of the complex plane. So now we're going to calculate EY. Now this is the thing that took us about 15 minutes earlier. Okay, so calculate EY, and so EY, I'm just going to call it E, is Q, and now we normally write I times Y, but sometimes that can introduce bugs. So what I tend to do is always explicitly state one I for when we need our imaginary number. So the EY was QIY times Q minus IY. And from that we subtract P of IY multiplied by P minus I times Y. Okay, so if we run that, so it's moaning about Y because I haven't defined the symbolic variable Y. So I do sims Y, and then it will symbolically determine what E is. Right, so you can see here, E is 0. So this still satisfies that second criterion. The second criterion was that E was always greater than or equal to 0. So the fact that this is 0 means that the second criterion is passed. And we saw here that the first criterion is passed. Therefore, we have what's called an astable method. And an astable method, as I mentioned earlier, is one where there's no limit to the step size you can use. So you can use a large step size, but you've got to be careful, because obviously the larger the step length you use, the more inaccurate your results are. So with an astable method, you can use a large step length, but you might end up having an inaccurate solution. It will be stable, but it might be inaccurate. Now, the reason why astable methods are so useful is because we can have what's called stiff problems, and stiff problems are where you've got a really stringent stability constraints on H. So if you got, for example, a non-astable method, you might have to use really small values for step length, which means you're doing lots and lots of calculation, or you can use an astable method and a sensible step length, and it will still give you a solution. Okay, are there any questions about what I've just shown you on MATLAB? Yeah, I mean, I was just having a look at some of the other questions. They're fairly similar. Would to plot the region of absolute stability? Okay, what do I mean by that? Well, if you've watched the lecture videos, okay, if I just scroll all the way back up. So this is the definition of absolute stability. So I mentioned this in the lecture videos. Okay, so now the stability function for the Euler method is 1 plus z, and we saw that earlier. And what we're going to do is I'm going to just generate, or I'm going to do what we call plot the stability function for a, plot the stability region for the Euler method. Okay, so that's what I'm going to do here. If I just okay, so in Blue Peter style, I've got one which I created earlier, which I'm going to show you. Okay, so you're not going to want to watch me sort of type all this out. So, okay, so I've copied and pasted something in. So I just explain what I've done here. Okay, so our stability function is what we're doing to our current solution to get our next solution, and that's for the test ODE. Okay, now for our method to be stable, we need the growth in the error, which is given by RZ, to be less than or equal to 1. So what we do is we plot the contour where it is equal to 1, and that's the boundary of the stability region. So in this code, what we've got here is I generate a single an array of x values from -5 to 5, 100 of them. So lin space stands for linearly spaced values. So these will all be equally spaced, and I've done the same for y. Then I've used a mesh grid command, and now this just converts the 1D arrays, x and y, to 2D arrays. Okay, so, and then I calculate the complex number. So x is a real number, real part, y is the imaginary part. So this gives me z. So that's my complex number. Then I define the stability function, and I've used the stability function for the Euler method, which is 1 plus z. And then what I've done is I've used a filled contour. So contour F means a filled contour because I want to fill in the interior. Abs R, well, that's the modulus of our stability function. And this here says, okay, I want just one contour line at where abs R is equal to 1. So if I run that code, you can see here we have the stability, or what we call the region of absolute stability for the Euler method. Okay, so what this means is if we're solving this test ODE, for a value of h would have to be within this, what we call the interval of absolute stability along this along the real line here. Okay, different methods have different regions of absolute stability. So for example, if I just change this and I make this into the fourth order method, plus 1 over 24. So this is the fourth order series expansion of E, which is the same as the stability function for the ERK method. Run that again. Oh, I'm sort of zoomed in a bit too far there. So what I'm going to do is using the axes command, I'm just going to zoom out a bit. Let's see. There we go. So that's the region of absolute stability for, well, it's not for the Euler method. This one's for the RK4 method. Okay, so you can see it's actually a fourth order method. It's got a bigger interval of absolute stability than the Euler method. Okay. Right. Last thing I want to show you, and just go back to that page. I should have, to be honest, I should have really started with this, so my apologies. Up here, okay, here's an example of a solution using the Euler method for the ODE y dash equals minus 2.3y. Okay, so what I'm going to do here is actually, I'm only going to plot one at a time. So I want to show you something specific. Okay, so let's say I've got a fairly small value for h. Oh, I've got too many legend entries. Okay, so I'm just going to just get rid of the legend. That's probably the wisest thing to do. Okay, so I've used a fairly small, I say fairly small, value of h at 0.1. You can see it roughly follows the solution of the black line there. If I was to use a larger value of h, let's say I think it's 0.7 in the notes which I've used, you can see, okay, it's not a very good approximation, but it's still stable. So what's happening here is our solution isn't sort of shooting off to infinity. But if I increase the value, so let's say just to something like 0.9. Okay, so what's happening here is we have an unstable solution. So the errors are actually growing. So you can see the errors between the computed value and the actual value, they're actually growing. So this is an unstable solution. Now, for y equals 0.7, we had a stable solution. For y equals 0.9, we had an unstable solution. And if we examine the interval of absolute stability, which I have done further down the notes, oops. Okay, the interval of absolute stability with the Euler method gives us this constraint here. So this is, I must stress, this is specifically for the Euler method and just for the test ODE. We had h is less than minus 2 over lambda. Now, in our example we just looked at, lambda was minus 2.3. So therefore, h is less than 2 over 2.3, which is 0.8696. Okay. Okay, right. So that's what I wanted to cover in that session today. And tomorrow we're going to be looking at boundary value problems, which is another similar to our initial value problems. So we're going to be looking at solving boundary value problems. Next week we're going to switch tact a bit, and we're going to be looking at solutions of linear systems. Okay, so now's your opportunity. Any questions you have? If not, we'll call it a day there on this webinar.